Work through an example of an elevator. We're given the weight of the elevator, 27,800 newtons. In one case, the elevator is speeding up because it's moving upward, and we're given its acceleration. And then in the other case, we are having an elevator that's moving up but is slowing down at the same time. And in that case, in both cases, we're trying to solve for the tension in the cable that's supporting the elevator. Let's start off with a free body diagram for the elevator, and we'll do the speeding up case first. So, a free body diagram, I'm not any great artist, so I'm just going to have a block representing the elevator. I do want to be careful and pick a coordinate direction though, because I'm going to write out some vectors here in a second, and when I write those vectors out in components, that's going to be in reference to this coordinate axis. So I'm picking up to be my positive direction. So some things that we know. We know that this elevator is accelerating upwards. So there is acceleration vector. And we also know that this elevator is on Earth, so there's going to be a force of gravity exerted on it. We're even given what its value was. So I'm going to put in a vector for the force of gravity, and there's also going to be a force of tension from the cable on the elevator, and that force of tension, I'm going to draw a vector that is even longer than the force of gravity, so I have to wind up with a net force that points upwards, because the net force is going to be parallel to the acceleration, which points up. All right, let's work some things out. Writing out Newton's second law of motion, I add up all of the forces on the elevator, and that equals the mass times the acceleration of the elevator. When I do that in my chosen coordinates, the tension vector is parallel to the acceleration, so those point in the same direction. Force of gravity points in the opposite direction. So we're going to have tension minus the weight is equal to mass times acceleration of the elevator. And we're asked to solve for the tension, so I just have to move the weight to the other side. So the tension is going to equal the weight plus mass times acceleration, and I can rewrite this. This mass is the weight of the elevator divided by the acceleration due to gravity. So I can rewrite this as tension is equal to the weight plus the weight over the mass. No, sorry. We rewrite it as the mass is the weight over the acceleration due to gravity. So we've got a little g, and then times a. So just substituting for what the mass m is. Both those terms have the force of gravity in it, so I can factor that out. So factor out the weight, and we have 1 plus a over the acceleration due to Earth's gravity. And I know everything in that, so we can actually just calculate a number. And when I did that, if I did that correctly, we'll have the tension when the elevator is accelerating upwards at 1.22 meters per second squared is 2.78 times 10 to the 4th newtons, and I'll have 1 plus 1.22 over little g is 9.81 to 3 digits. And then I'm not going to worry about the units because they clearly are going to cancel out. Is 1.22 meters per second squared over 9.81 meters per second squared, and the meters per second squared cancel out. So in this case, the tension in the cable is 3.13 times 10 to the 4th newtons. And we also need to do this then for the case when the elevator is slowing down. So some things are going to be similar, some things are going to be a little different. We want to make sure we understand what the differences are. So same positive coordinate direction is up. And have my elevator and my free body diagram. I know that the acceleration points down. So I put in my acceleration vector, which is the same direction as the net force. So now the force of gravity, it's the same weight of the elevator, so I should draw that vector to be, at least within my abilities, the same length as that one. I'm not going to worry and get a ruler out, but that looks about right. So to get a net force down, I'm going to have a tension that is smaller than the weight. All right, and then going through the analysis that we're going to do for Newton's second law of motion, the acceleration is parallel to the force of gravity, or to the weight. So these two are going to come into the equation with the same sign, or point in the same direction. So in the case of slowing down, so it's moving up, the acceleration points down. Newton's second law of motion is going to tell us that we have the tension pointing up in our coordinates, the weight pointing down, and that is equal to mass times acceleration. The acceleration, when I put it in, is going to come in with a minus 1.22, because pointing down, I picked up to be the positive direction. All right, so same sort of thing. I'm going to move the weight to the other side. Tension is going to equal the weight plus mass times acceleration. We're going to play our same little game of eliminating the mass in terms of the weight divided by the acceleration due to gravity. So we'll have force of gravity plus force of gravity over the acceleration due to gravity times our acceleration. We can factor out the weight just like before. So far everything looks the same. And now let's put in numbers to finish off our equation. The tension is going to equal the weight, which is still the same, 2.78 times 10 to the 4th newtons. I have a 1, and then now I'm going to have a minus because I picked up to be the positive direction, but my acceleration points down. I have minus 1.22 or 9.81, and this is going to give me, when I put that in a calculator, I got 2.43 times 10 to the 4th newtons. And just back up to make sure this makes sense. When the elevator is moving up and speeding up, the tension in the cable pulls the elevator up with a force greater than its weight. And then when the elevator is moving up but slowing down, so velocity and acceleration point in opposite directions, the tension in the cable is less than the weight. So it's the force of gravity that is slowing the elevator down in that case. And we wind up with when the elevator is moving up and speeding up, tension greater than its weight, and when it is moving up but slowing down, a tension that is less than the weight of the elevator. And those both make sense.